next speaker, Laurent Cavalier. Model selection is sparse heterogeneous framework.
So first, I would like to thank the organizer. I'm very glad to be here. And concerning the session, it's related to the first talk by Laurent Cavalier. So I choose the word heterogeneous, but you may replace it by heteroscedastic. The problem that we deal with are not exactly the same, but still we are in the heterogeneous framework. So it's a joint work, by the way, with Marcus Rice, who is there. Okay, so first, the model that we consider, rather simple model. So we have our data X, we observe a function in RD, and we had a Gaussian nodes. And we have the idea that we would like to project, that we are able to project onto some good basis. I will explain what. So then what we get if we go to the coefficient space, so the sequence space model, so the space of coefficient, by projection we observe a sequence of x lambda equal to f lambda plus psi lambda for the whole lambda. And psi lambda are the projection of psi, the Gaussian noise, onto this basis. And we assume that's the assumption here. One of the strong assumptions here is that the covariance matrix of psi lambda as a vector is diagonal. So, and that we have heterogeneous sigma lambda might be different usually. So we might think usually of sigma lambda increasing, but the main results are valid for any kind of sigma lambda.
But they are uncorrelated.
They are uncorrelated. That's the assumption. So that's the main assumption. So we deal with the heterogeneous framework, but for the diagonal case. That's why we say that we are able to choose a good basis. Okay, so I will just say a few words about how to get such an example. I will come back after the result on this, but clearly we have in mind the idea of an inverse problem in statistics, or a model of inverse problem in statistics where we use the SVD in order to get some kind of result, or a model of fractional Brownian motion, so where we observe your data with a fractional Brownian motion instead of a Brownian motion, and then you may get this kind of sequence space. But first, I will go into the math, into the result, and to the method, and then I will go after to the examples. Okay, so the estimator that we consider is quite simple. So we would like to estimate f lambda. That's our goal. So we know exactly sigma, so it's different from the talk from Arnac. Our goal is to estimate f and then its coefficient. And our estimate is the following. So it's really a model selection point of view in the sense that we have the possibility of either keeping coefficient and use the empirical observation in order to estimate the coefficient, or either to kill, to eliminate the coefficient. So we have only two choices. So it's really a matter of keep or kill each coefficient. It seems that the family of estimator is simple, but from a model selection point of view, it's not that simple. In fact, I will explain why. And the empirical version, so if you keep the old data, you get the FTO, if you keep the old sequence. Okay, so now, from a model, I fix the notation. So as I said, it's a model selection point of view. Okay, model selection, there is plenty of model selection point of view. So mainly here, and mainly talking of model selection linked to the work of Birger and Sarr, Akaike, Mallows, and so on, all this topic of model selection. but here I will be more precise. So concerning the notation, so we keep we fix absolute value of lambda as the number of coefficients that we keep. N is the size of the family, lambda, and we denote by sigma h the matrix restricted to the coefficient that we keep. So with different variance in each coefficient. That's really one of the main points, is that there is really a different variance in each coefficient, but we know the variance. Okay, I will fix the notation of the norm of A as the operator norm, that is for matrix the largest eigenvalue. Okay, and here the point of view is really model selection, so we fix a family of possible choice. It may vary from time to time, but we may get results for possible family of choice of H, in capital H. So it's really a model selection point of view, but as I said, the family is simple, but the family is quite important. Even if the family of estimator it's a large collection of estimator. And why? Because for each coefficient you may decide to keep or not, and at the end of the day you get a 2 to the power n as the size of as the different possible choice that you get. Okay, and that's the main idea, and that's why you have to choose a penalty more carefully, and a stronger penalty than, for example, as we explained, the AKK penalty or this kind of penalty. So here, what we define, we deal with the penalized empirical risk. So we minimize this risk. So it's a penalized risk. So to the left, you have the empirical risk. Sorry, and to the right, you have the penalty. And you balance among this family of H, and you minimize it in order to get your estimate. And we get an explicit penalty, we get this penalty. So the form is slightly more difficult because we have variance which might be different. So we have to reorder the variance, sigma, lambda, and so on. So the penalty depends, that's the whole story. So we have to take care about the number of coefficients that we keep, but also about the variance in each coefficient. So the problem is not all symmetric. That's one of the problems. So the penalty depends on both the number of coefficients that you keep, but also on the position. Okay, and then we minimize, and we obtain this estimate.
So just to clarify, sigma square sub bracket j sub h. Is the largest variance on the block if defined by h?
Yeah, on the block where I keep the block. It's not really a block. The one that I keep.
Yeah, but the subset. So it's the largest index of the set.
Exactly.
But you cannot depend on the order. So how your order is defined? So you just I mean, what means this bracket in J? So how you order you selected the coefficients?
There. So
Yeah, you can always assume that you order the variances.
You know the penalty. You only keep the penalty where you put that you want to keep, the one with the h lambda equal to 1, and then you order. But it's not a block in the sense that it's a block, but not a following block, not a block time.
But if you order from the beginning by sigma, then that would be the usual order, isn't it?
Yeah, exactly. Okay, so I will discuss about this penalty and compare with the homogeneous case, but still the idea is that the penalty is much larger than the AKK penalty, so it's more in the spirit of the penalty of a constant time log k log n over k when you go into, if you go into, for example, the model of the simple model of a regression, linear regression, where you have to select a number of variables, so you have p variables to select, and you have to, and you need this kind of penalty, which really are stronger than the AKK penalty or this kind of penalty. That's one of the main points. Okay, what we may get is this kind of result, so that's one of the first results. So we get to the left side, so the risk of our estimator, we get something like, so with to the right, we have, it is sharp in the sense that delta may be as close as 0 as I like. It's not exactly sharp, it depends, but it's considered to be sharp, so because the constant is as close as 1 as I like. Here you have the minimum among h, so you have the bias term and so on, so you have the penalty, so it's mainly the risk. You have a remainder term, slightly different from usual, but still it's a good, it appears that in fact it's a rather good remainder term. So this result is non-asymptotic, so it's valid for the moment. I've not specified the functional class that I consider.
I mean, in terms of Oracle, I'd like to see on the right-hand side something that tells me the minimum distance over all linear estimators of the 4H. So which part is that? The entire inf? No.
No, because here it's here.
But whatever is before the penalty, is that the risk of h lambda times?
Yeah, this
times
is the
x?
bias. It's written in a slightly different way, but this is the bias. This is the minus the variance, but the variance is inside the penalty. So here you really have the risk of a projection estimator.
I think your penalty is much larger than the variance.
Yeah, the penalty is much larger than.
So
You're right.
in this sense, it's not risk adaptive. So within all factor, I guess.
Yeah, sure. What do you mean? Oh, yeah, but I will go to the sparse. For the moment, I don't have any assumption.
No, but first, what is your script H? Is it the set of all subsets?
It might depend. So we use it in both ways. So it might be the set of the full subset model selection that I will present, but it might be also the set of threshold that I will not present, but it's also a special case. Quite related, I agree, but not exactly.
Your penalty is tailored to this set of all subsets. If it's smaller, but maybe you can improve the penalty. Because the penalty is quite strong. So it's
That's the problem.
Yes.
That's what I said. So, okay, if we go to model selection, so it's a large family, and it's a so large family that, in fact, if you go into standard linear regression, if you consider a model with 50 variables, so it's not a lot, because in standard linear regression, you put usually plenty of variables. So any product, any square, any whatever you like, are new variables. So it's quite common to have something like 50. And then usually, with your computer, you are not even able to minimize this criteria. That's why usually, in this case, you don't even use ARC, BRC, but forward or backward method algorithms which are not exactly the same. So, and I really agree that this difficulty from a numerical point of view is exactly the same that we have into the statistical part. So the family is large, even simple, but still large, and then you have to deal with it. So, okay. But our space of coefficient is quite good. I will present it here. Okay, so I'm using the same notation than Arnac, so I use the same sparse family of representation, so it's okay. I don't have to present too much sparsity, so it's well known, so there's plenty of ways to get sparsity. And for example, we choose the same notation, not the same notation, but the same class, so we consider a class of coefficient. We suppose that the function f lambda had a maximal proportion of non-zero coefficients. So it's really, we have a finite number, finite that may tend to infinity with n, sure. And this, we call this gamma n, the maximum divided by n, as this maximal proportion. So we think that we have n, we tend to have n gamma n coefficients, which are really different from 0. Okay, usually. Gamma n is going to 0, as in the paper of Abramovich and so on. And n gamma n tend to infinity. So it might be sparse, but not too sparse. So this is quite standard. Okay, it's With this kind of assumption, we may deal with the full subset model selection. So really, the full family of coefficients. We minimize this criteria, and we get a result. So get a result which is built on the previous result. It's not exactly a minimax result, not exactly written like that, but it looks like a minimax result. So what we get is that when n to going to infinity, this result now is asymptotic. Then we get the first upper bound. Perhaps, okay, there is a different term and a remainder term. Okay, perhaps it's more easy to go there. So we may get that in the case where the sigma are increasing in a polynomial way, so we may, as I will explain this, we may think of inverse problems, standard inverse problem. We may get this kind of result. So we have constant 4, which is quite important. We have the n gamma n log n.
Sorry, what is norm of sigma? It's not the spectral norm?
The norm is the maximal eigenvalue. So since it's diagonal, it's the maximum.
Oh, it's the maximum.
Yeah. So here, as I said, it's a kind of oracle because it's the one with the true good coefficient. So it knows, this one knows exactly where are the true non-null coefficients. Okay. And okay, the 4 is quite important here. And the form is, I will comment and compare with the homogeneous case. Now we have a minimax lower bound. Okay, so it's good for Christophe. So it's in the full form here, just for use, with the explicit family. So here is really a minimax lower bound. So we have the maximal risk, and we have the risk for any possible estimator. There is a choice here, so that there is different weights that might be obtained. So, but what is more important is that we are able to get this kind of result with this. Okay, so the lower bound is the following. So that we get almost the same in the previous result, except that we have a 2 here instead of 4. And
excuse me, Laurent, there is an infinity norm again there. Lower bound.
sorry.
This is the norm of sigma, yes.
Yeah, this is the normal sigma.
Is it an infinity norm again?
Yeah, sure, always. It's a strange stuff that happens in the minimax world, is that you don't know where your true coefficients are, but if you go into the minimax lower bound, then your worst case scenario will go to the worst
You
variance.
could restrict your
But
box at
maybe
0, right?
there is only one coefficient. Like this.
Yeah.
And all the others are much smaller.
Let's see.
But you pay only once this price.
Yeah,
There
but
will be
as-
this n times gamma.
At the end, well, if you, yeah, but if you consider it's in this worst case. So there, you may change. There is different way to get result. So if you have a special case, but if one corollary is to get there, but it's just a corollary. That's where we explicit, and we have several versions depending on its kind of disadvantage. Okay, so it's almost sharp, almost, because we replace a force by a 2. Okay, I will compare with result in a heterogeneous case. So there is some paper in this really close to it. So there is a paper, book by the way, by Ian Johnson, so in 2011, and it's written in a more general form. So it's really written in the Birger-Mersat way, so it's really a penalty and so on. So then there is this kind of stuff. There is also a paper by Rocher, slightly in the same spirit. Paper by Arnac, but not so related, in the same context, more general, but not exactly the same reason, I hope. Okay. Anyway, in any case, usually the bad news that if you consider usually this more general situation, then usually what you get is a constant, universal constant in front of the oracle, and that's not so bad. But the problem is that you also have a universal constant, usually difficult to calibrate, inside your penalty, and that's more difficult to deal with. So the good news is that by using this, we have a penalty which is explicit. It's not exactly the optimal penalty, but because we don't get the exact result, but it's close to the real penalty.
Is that because it's hard to calibrate and you did not calibrate it well?
Yeah.
Okay.
But there is, perhaps, there is hope. I don't know. If you go to the homogeneous case, there is many works on this topic, so a lot of work on model selection, plenty of AIC, BIC. This is more related to the RIC, so it's a specific penalty. So there is also, for one node, there is a lot of paper on false discovery rate, and again, it might be seen as a model selection point of view and in any of these results, usually again there is constant or something to choose in order to get the result. Okay. The closer paper is the one to our work is the one by Yuri, so that's why there is hope that I don't know. So there is a paper by Yuri Globev in the homogeneous case, so, and he got an explicit optimal thing to be optimal penalty with the constant 2 instead of the 4. So our penalty is, the contexts are different, but our penalty looks like twice the optimal penalty, and we lose a 2 in the result, but still only in the constant. Okay, so I think that there is interesting difficulties in this framework. So one reason is that usually in all this topic, usually you only deal with, you may do FDR or model selection or whatever. The only main point is how many coefficients you keep. So it's really a symmetric point of view. You don't care too much about which coefficient you keep. Here it's not the same. So everything depends on the one that you select. So the penalty should depend on the place that you keep, and the minimax down also, and so on, and the process also, and the stochastic process that you have to control is more difficult to control, I think. So that's perhaps one of the reasons. So that's the idea that there is no symmetry, and okay, there is a lot of game to play with this penalty, depending not only on the number of coefficients, but also, as I said, on the variance and the position and the level where you put the penalty. And we see it also in the results. So the results are, there is some strange effect in the results if you consider the minimax point of view, and not the minimax point of view, but just more carefully the viewpoint. Okay, so okay, so some example. I just one slide, say 2 slides on one example that we have in mind. So there are other examples. So one of the examples that we have in mind is the following. So we suppose that we have an inverse problem. So equals with a operator that is injective, compact, and so on. So we have a noise level, we have a Gaussian white noise, and we may use the SVD of a compact operator here to diagonalize the operator. That's a way to do. And if we do it carefully, that's exactly what we want. If you project, we get two bases related to the operator. We know exactly the good basis here. We project on the good basis, and then what we get is a diagonal in this situation. So what we get is the following. So it's exactly with the notation what we get before, with the idea that the singular value, which are going to 0 since the operator is compact, here are the variance. 1 over the eigenvalue are the variance. Okay. So that's one example, standard example that we have in mind. And in this standard example, the problem is that usually sigma lambda is increasing, is increasing to infinity. So that's one example. Another example, but I will skip. Sorry. So in order to conclude, so as a conclusion, first conclusion, so we get almost sharp Minimax result. The estimator is fully adaptive. What I mean by fully is that it's adaptive, we don't know the sparsity or whatever, and fully in the sense that there is no constant to calibrate. So the penalty is explicit, you may use into the simulation. It's not exactly optimal, it's not optimal, but still you may use it. We get an explicit penalty. We had a result for family of thresholds, which is a very natural family to consider here, because the good news is that the threshold family thresholding is quite easy to compute from a numerical point of view, not as model selection. Concerning the penalty, so I think that Yuri was quite pessimistic. So what do you think, Yuri? So is it possible to get the optimal penalty? So the paper by Yuri is quite involved. There was a first version of the paper and the second version of the paper with really strong result, but it's really built on plenty of ideas that are not exactly easy to implement here. So I don't know. So that would be possible extension would be nice also. Extension to the non-diagonal case. So the idea of extending replaces, for example, the SVD by the WVD, for example, that they get decomposition. Okay, that's all. Thank you.
So how does it compare with the, you can probably directly apply the results of that on San Juan, that, right?
I don't know. So I was not aware of the result.
Come on, yeah, you know about
the previous group. Okay, no. So the results of the Arnac and Salmon are different because they are considering all the linear smoothness. So it's really, here the difference is that it's built on the Riscal approach also, which is behind. But the difference, as Cavalier said, is that if you have a family of all the linear smoothness, or what in Virginia Massar world they call a small collection of models, then you have a penalty term which is Akaike. And if you go into the Riscal, you have a penalty of the second order. But here you are in a different world where you have a model selection. So the family is large, so it's an exponential family of
You have an exponential family. You can take any fine estimator in any family you want.
Yeah, but then you are in the order process. So here the difference is that if you go into the model selection, then the second term, even by the Riscal, that's what happened here, you have to pay to penalize more with this log term. That's why there is so many results in this penalty. And they are good results because many people are using AIC in the case of variable selection. So, and AIC is not built for that. The family is too large. I mean, if you use a computer, you see it. That's why there is this forward backward method. Because even minimizing the AIC with a family of 50, even 50, I mean, 50 variables is not so much in linear regression because you put what you like in linear regression. So we might compare, but not with this result. So more with the other results.
That's exactly my point. Why do you consider the figures of all subsets? So it's too big. For your example, it's very unreasonable to consider because you have nature order. Why we should take all coefficients with huge variance? So, I mean, it's very natural to take projection estimators, which are the first key for F, and then you can do it almost risk unbiased.
It's true, but I would be slightly rude. It's already done. So that's exactly what we have done with Yuri. So
Okay. I see.
Yeah, I agree. That's so the problem with model selection is that the good news is that the problem in math is exactly the same with the computer. So the family is simple, but for any variable it's not nested family. So for any variable you may keep or kill the variable, and you change the penalty at each time and so on. So and then you have to penalize more. Okay, you're gonna sound know it for a while and so on. So that's why. So there is a lot of. But perhaps it's one of the limit. I don't.
Okay. So thank you very much.